Unit 3 Review Chemistry. You can find this review and this video at srhschem.wikispaces.com and on YouTube at channel LEFFELlabs. First question asks us to draw a Lewis diagram of NaCl. So first thing you have to note about NaCl is that this is an ionic compound, which means that drawing the Lewis structure is going to be fairly straightforward. So first we have to figure out how many valence electrons sodium and chlorine each have. So on the table of elements, everything in the first column has 1 valence electron, everything in the second column has 2, and then 3, 4, 5, 6, 7, and 8, and so on. In the middle, we have our transition metals, so we don't know how many valence electrons they have. So we find that sodium is in the first column, which means that it has 1 valence electron. And we find that chlorine is in the 17th column, which means that it has 7 valence electrons. So in an ionic compound, one atom gives away its electron to the other atom. In this case, sodium is going to give away that 1 valence electron to chlorine, so they will both have full octets. So there's chlorine with its 7 valence electrons, and there's sodium's 1. Since sodium lost a valence electron, its charge is going to be +1. Because chlorine gained a negative electron, its charge is -1. The way the atoms interact whenever they form a bond is that one atom gives away electrons. That atom becomes positive. The other atom gains electrons. This atom becomes negative. Opposite charges, the cation and anion, are going to attract, and that is the formation of the ionic bond. Next, we have to draw a Lewis diagram of carbon tetrachloride. So because this is a covalent compound, we got a few more steps. Because we could have single, double, or triple bonds, we got to make sure that we calculate the number of bonds that we have so we draw it correctly in the Lewis dot structure. So first, we figure out the number of valence electrons that we have. By itself, carbon has 4 valence electrons. In the formula, there is 1 carbon, so I'm going to multiply that 4 by 1. Chlorine has 7 valence electrons, but there's 4 of them, CCl4, so I'm going to multiply 7 by 4 to get 28, and the total is 32. Next, I have to figure out the number of valence electrons that I would like to have, or the number that I need. Carbon would like to have a full octet, that means 8 valence electrons. I'm going to multiply that by 1 because in the formula there's 1 carbon. Chlorine would like to have 8 valence electrons, and I'm going to multiply that by 4 because in the formula it's CCl4. So that gives me a total of 40. The next step is to figure out the number of bonds that I have. So I do 40 minus 32. That tells me that I'm short 8 electrons. And I divide by 2 because there's 2 electrons in a bond. So that gives me 4 bonds. So even though this compound only has 32 electrons, it's going to share in such a way that it's like it has 40. Next, I have to figure out the central atom. So your choices are carbon with 4 or chlorine with 7. So it's going to be carbon with 4. It's always the lowest number of valence electrons because that atom can form the most bonds, but it's never going to be hydrogen. So next, we draw the skeleton and the Lewis structure. So we just established that carbon is the central atom. We also know from the formula that I have to attach 4 chlorines to that carbon. And we also found out that I can do this using a total of 4 bonds. So these are all single bonds, which means 2 electrons. A double bond would be 4 electrons, and a triple bond would be 6 electrons. So each of these double bonds is 2 electrons being shared. One has to come from carbon, and one has to come from chlorine. So for each of these single bonds, I'm putting 2 electrons in, one from carbon, one from chlorine. And I'm using different shapes so we can tell which electrons belong to which atom. Now I got to go and double check. Carbon by itself should have 4, and we drew 4 blue dots for carbon. Chlorine by itself should have 7, and for each chlorine I've only drawn 1 X, which means that each chlorine is short 6 electrons. So I'm going to add these 6 electrons around the chlorine. The way atoms interact in a covalent bond, in this case carbon is sharing each of its 4 valence electrons with chloride, and each chloride is sharing one of its 7 electrons with carbon. So even though we only have 32 electrons, the atoms are sharing in such a way that it's like they have 40. And the sharing of these electrons is what forms the covalent bond. The next question asks us about the different bond types and their properties. So let's start with metals. Here I have a bunch of aluminum atoms. And whenever a bunch of aluminum atoms get together, they form metallic bonds. They each give up their 3 valence electrons. If you lose 3 negative electrons, you get a +3 charge. These electrons are given up to the electron sea. This structure explains the properties of metallic bonds. Metals have high melting and boiling points because of the strong attraction between these cations, the +3 charges, and the electron sea. So I need a lot of heat energy to break up those attractions and melt the metal. Metals have good conductivity. This is because the electrons in the electron sea are able to flow. So they're free to flow and they can carry electric current or heat with them. And the state of matter of most metals is going to be solid, and this is again due to those strong attractions between the cations and the electron sea. The notable exception here would be mercury. Now let's consider ionic bonds. So here I have some sodium and chlorine atoms together, and in an ionic bond, the metal, in this case sodium, is going to give away an electron to chlorine. That makes sodium have a +1 charge and chlorine have a -1 charge, and this will happen throughout the ionic crystal. This explains the properties of ionic compounds. They have high melting and boiling points because there is a very strong attraction between the cations and the anions. It takes a lot of heat energy to break apart those attractions. There is no conductivity in an ionic compound because the charges are stuck in place. They are unable to flow or to carry electric current. And the state of matter is going to be solid, and this is again just due to those very strong attractions between cations and anions. Next is covalent bonds. So a covalent bond occurs whenever atoms share electrons. So here I have water. So in these covalent single bonds, 1 electron from oxygen, 1 from hydrogen. And oxygen also has 2 lone pair of electrons. So ionic compounds have very high melting points, whereas covalent compounds have very low melting points. This is because there are distinct molecules in a covalent compound. So each of these is a distinct molecule, and the attractions between them are fairly weak. So in this case, I'm drawing in some hydrogen bonds, but the attractions between these are much weaker than the attractions between atoms in a bond. Therefore, they're easier to separate, making them easier to boil or to melt. There is no conductivity because there is no charges in covalent bonds. This means that there's nothing to carry electric current. And the state of matter can be solid, liquid, or gas due to that weak attraction. The weaker the attraction, the less dense the state of matter will be. So something with very, very weak attractions would be a gas, whereas something with stronger attractions, like water, could be a solid or a liquid. Next is naming. So in this blue box, I've summarized the rules. So first thing you need to do whenever you're naming something is figure out which set of rules to follow. So this first one is an ionic compound, and I know that because I have Cu, copper, which is a metal, and I have SO3, which is a polyatomic ion. So Cu is copper. It says name the first metal, Romans show charge. So I got to figure out the charge on copper. The way we do that is by crisscross. So this 2 comes up here. So the charge on that is -2. And this whole thing, this SO3, is a polyatomic ion, which means what we're going to cross is this 1 after the polyatomic ion. That 3 is part of the polyatomic ion. That's not what we're going to change around. So if you have something with a polyatomic ion, it's a good idea to put it in parentheses just so you don't get confused. So that 1 comes up here. So the charge on copper is +1. So this compound is going to be copper 1, and SO3 is sulfite. So this is copper 1 sulfite. Next compound, once again, this is also going to be a polyatomic ion. This is also going to be an ionic compound. We know that because lead is a metal and chloride is a nonmetal. So in the case of a ionic compound with a transition metal, the Romans tell me the charge. That's another clue that I know that this is ionic. So there's lead. Its charge is +4. Chloride was once chlorine, and the charge on chlorine is -1. So whenever I crisscross, my formula is going to be PbCl4. The next compound, Na3PO4, this is going to be ionic because I have a metal, sodium, and I have a polyatomic ion. Sodium is not a transition metal, so I don't need to write charges. I know just by looking at the table of elements that the charge on sodium is +1. For a transition metal, I can look at the table of elements, but I don't know what charge those have, so I have to indicate with Roman numerals. So PO4, that is the polyatomic ion phosphate. So the name of this is simply sodium phosphate. The next is also ionic. I know that because sodium is a metal and sulfide is a nonmetal. So sodium is Na. Sulfide was once sulfur. So I just have to check the charges. The charges on sodium is +1. This is -2. Whenever I crisscross, my final formula is Na2S, sodium sulfide. Here we have our first covalent compound. I know that this is covalent because nitrogen and hydrogen are both nonmetals. So whenever it's covalent, we write the name of each element, changing the second element to end with "ide," and we use our prefixes. So first element is nitrogen. There's only one of them, so that would be mono, but we never start with mono, so it's just nitrogen. And then I have H3, so hydrogen becomes hydride. There's 3 of them, so that's trihydride. Okay, next I have an acid, and I know that this is an acid because it ends with the word acid. So quite obviously, this is going to be an acid. And the form that matches up to this is hydroblankic acid, which means that this middle part right here was once phosphide. So phosphide is just phosphorus. This is an acid, so it starts with an H. So now we just have to double check our charges. Whenever you have an acid, you need to check the charges just like a covalent, or just like an ionic compound. So the charge on hydrogen is +1. The charge on phosphorus is -3. So whenever you crisscross, your final formula is H3P, hydrophosphoric acid. This next one is also an acid, and I know that because it starts with H. So whenever I have an acid and I need to go from formula to name, I gotta look at the thing that isn't the H. So this thing is acetate. So my ending is 8, which means that this is going to become blankic acid. So instead of acetate, it becomes acetic acid. Once again, I have an acid, and I know that because it ends with acid. In this case, I have an us acid, so that corresponds to the ending originally being ite. So instead of chlorus, this was once chlorite. So chlorite is going to be ClO2. It's a polyatomic ion, and it's got a charge of -1. And it's an acid, so it starts with H. So whenever I crisscross, I get 1 and 1. So my formula is just HClO2. Next, I have another covalent compound. I've got nitrogen and oxygen, which are both nonmetals. There's 2 nitrogens, so this is dinitrogen. And oxygen becomes oxide, and there's 5 of them, so this is dinitrogen pentoxide. Silver bromide is an ionic compound. Silver is a metal, bromide is a nonmetal. Silver is in the middle with transition metals, but it's actually not. Silver always has a charge of +1. So silver is Ag with a +1 charge. Bromide was bromine with a -1 charge. So whenever I crisscross, my formula is just AgBr. Next compound, PbSO4. This is going to be ionic. I know that because lead is a metal, and SO4 is a polyatomic ion. So whenever I go to name this, I got to figure out the charge on Pb. So we can pretend that there's 1s after each of these. Now, this one's going to be tricky, because whenever I crisscross the charges, I get +1 and -1. That's actually not correct. If you look at the charge of sulfate, you see that sulfate has a charge of -2, which means that Pb must be +2. The reason this happens is because whenever you crisscross, you get 2 and 2, which is the same thing as 1 and 1, so it gets written as PbSO4, even though they each have a +2 and -2 charge. So this is lead 2, and SO4 is sulfate. The next one is also an ionic compound. I have a transition metal, I know that because I have Romans here, and a polyatomic ion. So titanium is Ti, and in this compound it has a +2 charge. Acetate is C2H3O2, and it has a -1 charge. So whenever I crisscross, my final formula is going to be Ti C2H3O2, and there's 2 of them. The next question is about the different bonding types. So an ionic bond is a compound composed of cations, which are positive, and anions, which are negative. A metallic bond occurs whenever there is an attraction between the free electrons in the electron sea to the metal cations. Polar covalent is a bond formed by unequal sharing of electrons, whereas nonpolar is formed by an equal sharing of electrons. Ionic compounds generally occur between metals and nonmetals, or there could be a polyatomic ion. Metallic bonds occur between metals. And covalent compounds are going to occur between nonmetals. In an ionic compound, one electron is transferred to another atom. In a metallic compound, the electrons are shared in an electron sea. And in covalent, they're just shared in bonds. So an example of an ionic compound would be like sodium chloride, table salt. Metallic compound could be brass or iron or steel. Polar covalent is going to be water, and nonpolar covalent would be oxygen. The next question asks us about the different VSEPR shapes. So what I recommend you do, draw in the electrons that are in the bonds. So for H and Cl, there's one from H and one from Cl. So there it is kind of rewritten. The number of bonding atoms to the central atom. Well, in this case, there isn't a central atom because there's only 2 atoms. The number of lone pairs, again, this doesn't apply because there's no central atom. So how do we figure out the shape of this? Well, I only have 2 atoms. And how do you connect 2 atoms? With a straight line. So the shape is going to be linear. Alright, so the next one is carbon dioxide. So there are 2 double bonds there. Each double bond means that we're dealing with 4 valence electrons. So half of them have to come from half of them have to come from carbon, and half of them have to come from oxygen. So I'm just going to fill those in. So carbon by itself has 4. We drew that in. And oxygen is supposed to have 6 each, so we have to add those. So this is what the Lewis structure for carbon dioxide would be. So if we look at this, the number of bonding atoms to central atoms. So this is asking for atoms, not electrons. So that means that there are 2. Lone pairs, those are going to be any electrons on the central atom that are not participating in a bond. So if we look at carbon's 4 valence electrons, we see that all of them are in a bond. So the lone pairs would be 0. Therefore, the shape of this, if we look it up on the VSEPR chart, is going to be linear. Alright, so the next one is NH3, which is ammonia. So if we draw in the electrons in those single bonds, that's what they look like. And then we've got that lone pair on top of nitrogen. So the number of bonding atoms to the central atom, there's 1, 2, 3 atoms bound to the central atom. And of nitrogen's 5 electrons, 2 of them are in a lone pair. So that means that I've got 1 lone pair. So the shape that this corresponds to is going to be pyramidal. The next question is about electronegativity and polarity. So to do this, you'll need the electronegativity table, and you need to know what the differences are. So for H and Cl, we take the value for chlorine, subtract it from H. If you get a negative number, that's okay. Just do the absolute value. So that's 0.9. So that is going to correspond to moderately polar covalent. For H and O, so that's 3.5 for oxygen minus 2.1. We just do the absolute value there. So that's going to give me 1.4, which is going to be very polar covalent. And for carbon, carbon has a value of 2.5. Hydrogen has a value of 2.1. So we subtract and we get 0.4, which is right on the edge of nonpolar and moderately polar. So nonpolar covalent or moderately polar covalent. Next question is about using symmetry to determine polarity. So if I can cut it in half and it's the same on both sides, then it is nonpolar. So symmetric, that means it's the same on both sides. That is nonpolar. Asymmetric, so A means without, so without symmetry is going to be polar. So if we look at H2O, if I cut it in half this way, it's the same on both sides. But if I cut it this way, we can see that it's different, so this would be polar. And for Cl2, no matter how I cut this, it's the same on both sides, so this is nonpolar. And this one right here, if we cut it in half, it's different on each side, so we want to say polar, but look at the charges. You don't have charges in covalent compounds. So this is actually an ionic compound. Ionic is like an extreme case of polar. Next question asks us which will dissolve in cyclohexane. So cyclohexane is nonpolar, and like dissolve like says only a nonpolar substance will dissolve in nonpolar cyclohexane. So we need to figure out which of these choices is nonpolar. They're all only 2 atoms, so we can quickly draw a picture here. And we see that if I cut these in half, this is the same on both sides. None of these are. So all of these guys are going to be either polar or ionic. So far, only iodide, I2, would dissolve in cyclohexane. We can also do this by subtracting the electronegativity values. So when we do that, we see that since this is 2 iodides, whenever we subtract them, we get a difference of 0. So this is definitely nonpolar covalent. So by inspection visually and from subtracting the electronegativity values, we see that the only thing that is nonpolar covalent is going to be I2. So the correct answer, I2, will dissolve in cyclohexane. Next is about the formation of ions. So the electron configuration for bromine, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Remember, the D block is a little bit more stable, so it actually jumps down in energy level. And then we have 4p5. So the highest energy level here is 4. And we see that in that energy level 4, the total number of valence electrons that I have is 7. This means that it's really close to having a full octet. So bromine is going to gain 1 more electron to get a full octet. Nonmetals tend to gain electrons, so the ion form is going to be bromide minus 1. Next we have aluminum. So in this case for aluminum, the highest energy level was energy level 3. So it's 1s2, 2s2, 2p6, 3s2, 3p1, which means that the total number of valence electrons is 3. So it's not even a little bit close to having a full octet. So it's going to be easier for it to lose those 3 valence electrons because the next lowest energy level 2, does have a full octet. Aluminum is a metal. Metals tend to lose electrons, so the ion is going to be aluminum plus 3. Potassium is another metal. In this case, the highest energy level is energy level 4. So the electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. So because this has 1 valence electron, if it lost that electron, the next highest energy level 3, has a full octet. So potassium wants to lose electrons. Metals are the ones that tend to lose electrons, so the ion formed is going to be K plus 1. Chlorine, the electron configuration is 1s2, 2s2, 2p6, 3s2, and 3p5. So that's the highest energy level, 3. And it has a total of 7 valence electrons, which means it just needs to gain 1 more. Nonmetals tend to gain electrons. So the ion formed is going to be Cl minus 1. So Br minus 1, anything that is negative is going to be an anion. So those are my anions. And my cations have a positive charge. So these two would be cations. Number 10 is about using the formulas and their charges to determine if the formula is correct. So first I have KMnO4. So MnO4 is a polyatomic ion. The charge on potassium is plus 1. MnO4 is minus 1. So whenever I crisscross these, I get KMnO4. So this one is good. For CaPO4, PO4 is a polyatomic ion. The charge on calcium is plus 2, and the charge on PO4 is minus 3, which means that whenever I crisscross, I should get Ca3PO4 but it's just written as CaPO4. So that is an incorrect formula. KOH, OH is a polyatomic ion. Potassium has a plus 1 charge. Hydroxide has a minus 1 charge. So whenever I crisscross these charges, I get 1 and 1. So that one works. NaCl2. The charge on Na is plus 1. Cl is -1. So this shouldn't be a 2. Whenever I crisscross, this should be a 1, which means that this formula is incorrect. Number 11, what are alloys and what are their usefulness? So alloys are mixtures of 2 or more metals, sometimes with small amounts of nonmetals as well. The reason this is useful is because it gives the metal certain desirable properties depending on what is added to it to make it an alloy. So surgical steel is mostly iron, but by adding these other things to it, like chromium, I get specific useful properties. Chromium gives the surgical steel scratch resistance, which is very important if you're using surgical tools. You don't want there to be any scratches where bacteria can grow. The nickel also gives it a smooth, polished finish. Carbon and molybdenum both add hardness. So alloys are useful because we can add things to a metal to give it the specific exact properties that we need. The Electron Sea Model. So in the Electron Sea Model, metals are going to be good conductors because the electrons are already free-flowing and able to carry electric current. They are also going to be malleable. If I hit a metal with a hammer, we see that the cations just slide past each other. So the cations are strongly attracted to the electron sea, and this allows them to slide past each other when hit with a hammer.